Alright, let's talk about your next lab, Lab 6. This will be a multi-week lab, and then there's definitely a reason for why I'm doing that, so do start early, okay? So this is going to be a C++ lab, where you are going to write a simulator for a CPU. So all those things we were talking about, like the fetch stage, the decode, execute, memory write back, you're going to model a CPU at that level. It's going to be really cool, alright? So I've made a silly CPU architecture called C45, obviously, for our class. And it's nothing like anything that exists in the world. It's a simple little CPU, but it works. It'll run any program you want to write. It's Turing complete, technically. So get all the files, and there's actually a folder that I've given you. If I go here, boop. So there's a folder full of a bunch of programs, too. We get a bunch of those, and that's what I'll be testing you on. So this is kind of what the programs look like. Program slash, I don't know. This is like the hello world program in this language. It's been compiled. I've made you the binary format, and I've also like given you the assembly. And I've also made like a little assembler. So these are the instructions in this language. It's gonna move an immediate into a register. Registers start with R's in this CPU. And then it's going to store the ASCII code for capital H. Okay, it's doing these things. Or sorry, excuse me. This is the ASCII code for H. Capital H is being stored into R0, and then it's storing R0 into memory. So I'm just hard coding memory addresses, memory addresses, memory addresses. So this is hello world. And then I'm loading it out of memory and printing each character. I have a print char assembly instruction because I made this CPU. We can simulate a CPU that has the ability to print a character out of a register. Why not? All right. So yeah, then the final there's like a stop the CPU. It's called the halt instruction, and that's supposed to stop it. So that's kind of what our programs look like. There's more where that came from. Like there's one that like count up. .c45 there's the assembly form at least, and yeah, it's like here's a loop. I am branching to like address 3, like this is instruction at address 0, address 1, address 2, address 3. That's how it's branching back. So yeah, that's kind of how that works. And cool. So isn't that fun? And @ signs are apparently the comments. That's what I invented, at least. All right. So enjoy the fruits of my labor. I've compiled all these to C45 machine code, so binary stuff. You're going to be reading the binary files and executing them. You're going to make it work, all right? So do read this entire thing, this entire write-up. Look at all the code. It's a little complicated, but it's going to be so satisfying to get it working, I promise. All right, so please completely read through every file I've given you, as well as this document. All right, so we're making a simulator that can read those binary programs that I pre-compiled for you, or pre-assembled, let's say, for this made-up CPU architecture, and we're going to execute them. We're going to pretend that we are the CPU in code, and we're going to execute them and make it work. So your job is to implement cpu.cpp. All right. Well, let's take a look at our CPU, our C45 CPU. Boop. So here's the header file, at least. Your job is to implement the implementation file, but here's some new things. So this is called an enum, or an enumeration, and it lets you make a bunch of little constants for yourself. Like this is the type called opcode, and these are the values in the type. So that's interesting. Go look that up if you've never seen it before. It's very useful. So this is a new thing in C++ that I'm forcing you to learn. Here's another enum that spans over the different kinds of registers that you would ever want to store in your code somewhere. And here's a struct that represents an instruction. We'll talk about that soon. Every instruction has an opcode. After you decode it, it has an opcode. It has potentially a destination register, some operand registers. You can also give an immediate value. All right. Not all of these pieces are going to be set when you're decoding, but like it's always going to be one or the other, or a couple. And then here's the CPU class, which you'll be implementing pieces of. All right, so like there's a constructor. We're doing this at a high level. We're doing it in C++, but still, we're simulating it. All right, so it has the ability to load a program. That's just a bunch of instructions, and each instruction is 32 bits long, so a bunch of ints encoded as binary stuff, right? The binary encoding of these assembly instructions, and then we want to be able to run the program. All right, and so like here's all the pieces of my CPU. Like we're going to make a simulation for the fetch stage, for the decode stage. helper for the decode, helpers for the execution stage, all that fun stuff, and then run program will take care of the rest. And then what does it mean to be a CPU? Like, what data are we holding on to? Well, we have a bunch of registers. We only are going to have 4 registers in our CPU, R0 through R3. We're going to have one flag for less than or equal to. We'll have that one kind of check when we compare. And then we also need to have a register for our current program counter, like where are we executing right now, PC, all right? That's going to hold the address of our current instruction. And then here's what memory looks like. We also are going to have the CPU keep track of its own memory. So we have 256 integers of memory, all right? 256 words, let's say, of memory. And same for instruction. This is data memory. We can store this much data in the data section, and then we can also have room for 256 instructions, because we're going to have 256 integers, right? Encoded in binary format, of course, but that is what's going on. So read all this, get more familiar with it, but yeah, look at all the fields to see what there is. So there's four 32-bit registers. There's one 8-bit program counter, because you can at most have 256 instructions anyway. Char is all you need there. There's one flag, LE for less than or equal to. 256 words of instruction memory, so that's 256 instructions total, and 256 words of data memory, so you have 256 places that you can write to or load from, store or load to, okay? So that's the idea. The only thing that's kind of different, that's like exceptionally different from our ARM CPU that we've been working on, is that the addresses, just to make things easier for you, the implementer of this simulator, all the addresses in the code will be for the entire word. So it's not byte addresses, all right? So if you try to go to data address 22 in assembly, like somebody told you to go there, it's really just go to data memory at index 22. It's every word. Like, you can only access words, not a single byte anymore. So that's to make it easier for you, all right? But with all this, you only need one flag, apparently. The CPU is Turing complete. If you gave it enough memory, which it might need more, but it can run any computation imaginable if you extended the instruction and data memory, surprisingly. It can do whatever you wanted. So that's really cool to think about. So you can run any program on this thing. It is not just a toy, all right? But it's very, very useful to learn how the CPU is working, right? So like I said, I've made a bunch of programs for you already, LS programs. Oops. Let's go out here again. So LS programs, so in that folder, these are a bunch of pre-compiled things, and you can make your own. I've made a compiler.cpp to generate from the S file to, should be called an assembler, shouldn't it? But still, this is a bunch of binary files that should be runnable on our fake CPU, all right? All these files are binary files. Your job is to read them and execute each individual instruction at like PC is your instruction memory, all right? So if I go quickly to the simulator file, simulator.cpp, its job is to kind of do most of this for you. You give it the name of the program you'd like to run, and then it's going to read in all the instructions. It's going to read all the bytes of that file in binary mode. It's going to open it in binary mode, read all the instructions, and add that to a vector of ints, right? Because each instruction is going to be 32 bits long, so ints. And then I'm going to load that program into my CPU. So I've done all that for you, and then I'm going to tell it to run. That's what the simulator is doing. So your job is to implement all the stuff from cpu.h in cpu.cpp, okay? So that's where we're going. But here's what every instruction looks like. Every time you fetch an instruction, you're going to be getting, right? Let's see, you're going to go and you're going to, in instruction memory, you'll get one unsigned int out, right? Each instruction is an int long, so 32 bits total. And here is what every instruction looks like. It has an opcode in the highest 8 bits, so in bits 24 through 31, all right? It has an opcode. It has potentially, it has a destination part in bits 16 through 23, if that is part of your instruction. Sometimes this is just blank, you don't actually use it, but this is what that part would encode. So bits 16 through 23 would store a destination. These are 8 bits. 8 bits for an opcode, 8 bits for a dest. 8 through 15, so another byte for an operand. Operand 1 goes there. And then bits 0 through 7, so the lowest byte of the int, is either a second operand, if it's like an operand that takes 2 registers, or it's an immediate value. It's a byte worth of an immediate value. Okay, so that's how that works. And here's what the instructions look like. So you read your opcode, like if you are the CPU, you're reading the opcode, you're getting a byte out, and then you're looking at what you see there to see what kind of instruction it was. That's your operation code. So there's 16 kinds in this pretend CPU. Right? There's a load opcode. That's opcode 0. It's for a load instruction. It is meant to load a immediate address. So this is the address. It's going to be in the immediate part. So bits 0 through 7 is going to hold an immediate value, not an operand 2. So take an address there. That's your address. Load whatever you see there. Go to data memory at that address and store it into this register. It's going to be the register encoded by the destination part. All right, so that's what that's going to look like. That's how that's going to work. Okay, same for store. It's going to take something in a register. So that's going to be the operand 1 register. Take whatever you have in there, CPU, and store it at the address given by the immediate part here. So you're going to interpret these bits as an immediate value, as an address into data memory. Okay. Then we have a move, so move a register into another register. So it's only going to use dest and operand 1. So that's opcode number 2. So if you see a 2 here, you're going to decode the dest and the operand 1 parts, and you're going to move this register's value into the destination register's value. Okay, so that's kind of how this is all going to be implemented. You have a move an immediate value into a destination register. That's opcode number 3. Add 2 registers. So that's going to use operand 1, operand 2, not an immediate. So 2 registers encoded, and then a 3rd register in dest. That's where you're going to add the answer into. That's opcode number 4. So you have that for subtraction, multiply, comparisons. Take the 2 operands and set the LE flag based on that. Then you've got branch if less than or equal to, branch always, a printing opcode, because why not? It's our CPU. We can have a printing opcode, an instruction that does printing for us in just one cycle. That's just going to go to this operand 1 register and print the value that's stored in the register. And then print char, instead of printing an int value, it's going to print a character value. It's going to interpret that register's value in operand 1 as a character value. And then finally, opcode 15 is halt. That's going to just stop the program. All right, that's meant to turn off the CPU essentially. All right, so yeah, this will make more sense as you read it. There's only 16 opcodes, and because of that, because we're using 8 bits to specify the opcode, we don't actually need those 8 bits. Okay, so we only need 16 opcodes, and so you only need 4 bits to represent one of 16 numbers. All right. So we're just going to use the rightmost 4 bits of the opcode section to encode which kind of instruction. All right, so like, I'll get to this example in a second, but do read all this yourself. So yeah, the dest part and the operand 1 sections, they're going to hold the encoding of a register always, and we're going to use for these guys as well as operand 2 when we get to it. 0 means we're looking at R0, the register R0. 1 means we're encoding R1. 2 means R2. And then 3 means R3. Because we only have 4 registers, we only need 2 bits for these things. We're not going to even care about the first 6 bits of these parts. Okay, so we're just going to look at the rightmost 2 bits. All right, that's how that works. And then the operand 2 / immediate can either be a register, in which case you'll look at just the rightmost 2 bits, or it's a full byte of an immediate value, in which case you'll look at all of it. All right, so here, for example, is how the add reg immediate R0, R1, 42 instruction would be encoded as bytes, all right, as a bunch of bits. That's this one. And it's going to take this register's value, add an immediate to it, and store it in this destination register. All right, so it's opcode number 5. And so the first X's, like, we don't care. We're just going to encode the number 5 in 4 bits in the rightmost part of this opcode section. So it's 0101 for 5. And the X's here are don't care bits. We call them don't care bits, which means they could be anything. They could be 1s or 0s. It doesn't matter. You're only looking at these bits to see that, oh, it was an add reg immediate instruction. All right, that's the idea. So you're going to need to zero out these if you're looking at stuff. So learn how to, you're going to do some bit twiddling with bitwise instructions to figure this stuff out. All right, so you're going to see the 5 here. You're going to not care about these. They could be 0s or 1s. You're just not going to even read them. You're going to get this out. Notice that it's a 5, which means, okay, now we're going to do add reg immediate, which means that this section, we're going to look for an immediate value rather than an operand 2. All right, because that's what it needs. And then R0 is going to be encoded as these 2 bits, so the number 0 for R0, the number 1 for R1 in these 2 bits. And these X's, again, could be set to anything. We're only looking at the rightmost 2 bits of these sections to notice which kinds of registers we're looking for. All right? And then the number 42 is going to take the entire immediate part of the blue section, of that last lowest byte in the int. And that's 42 apparently. All right? So that's add reg immediate, and that's what you're going to see each time you load an instruction. You're going to go and look at it. That's how you're going to decode it. You're going to go and look at those sections using bitwise operations. Okay, so I've written a bunch of programs. Here's like a program that counts up from like 1 to 100. All right, so you can see it doing stuff. See if you can figure out like why it's going to print from 1 to 100. These are addresses, by the way. BL4 goes to address 4, back to the start of the loop. Okay. And the number 10 is the new line character. That's why I'm putting that in R3. All right. So see if you can understand that. I've made an assembler. I've called it compiler for no good reason. That you can make your own, but I've pre-compiled everything else, pre-assembled, I guess. Okay. So yeah, what you're gonna do is, given all this knowledge, keep on reading this file. Like you're gonna be staring at this page for a while. I think. It's very, very important, all those opcodes and what they're going to be using and doing. Your job is to implement all of the execution of the CPU in the implementation file, cpu.cbp. All right. So what happens when you load a program? Like the simulator is loading this program. That's just the byte stream of instructions. It's going to load that. It's going to zero out all the registers. It's going to zero out all the data memory, and it's going to set the instruction memory it's going to zero it all out to halts, and then it's going to load instructions when we do load program. So it's just copying all the instructions into instruction memory. And the job of the CPU, right, we're going to say in the simulator, is going to be run programs. That's where it all starts executing and simulating itself. So if we go to that, that's going to be the first place you'll look. All right, scroll down to run program. This is the key. All right, so the very first thing you'll do is set PC to 0, because that's the first address. That's where the first instruction of your program is going to be loaded into. So set PC to 0. That's where it should start fetching from. And then it's your turn to write code that implements instruction fetching. You're going to get an instruction out of wherever PC is, right? Get the current encoded instruction out of PC. There's a method for that in the header file. See, it's fetch. Like, go to the address of PC, implement this, and that will give you the int encoded version of that instruction. It's just the bytes of that instruction. All right, so that's what fetch does. You'll call that with PC, and you'll of course have to implement fetch, wherever that is. So it's like go into that memory and fetch the binary form of that instruction. All right, that's how that works. And once you've got the binary form of that instruction, then you have to decode it. Yeah, that's how that works. We're also going to keep track of how many cycles we've done. You don't have to mess with that, but yeah, you'll also need to increment PC so that we're ready for the next instruction later, right? So it's just +1 to PC because that's a register. That's in the header file, right? Let's go back to the header file. There's PC. You can add 1 to it. Then you need to decode your instruction that you just read, right, into an actual instruction object. That's going to be useful for you. I guess I do want to keep this here. So every instruction, like this is the C++ encoding of an instruction. Like you want to make it pretty like this. You want to take your int, right, which is just a bunch of bytes. You want to decode it. Decode your encoded instruction with the decode function or decode helper method into an actual instruction object, because do you see how easy that is to like read off? Like you'll store the opcode, you'll figure out what opcode it was, and then put that here so that you can condition based on it in an if statement later. It's very helpful, all right? And then what I want you to do as you're decoding is just set all of these pieces, dest, operand 1, operand 2, immediate, because you're not actually sure yet which your instruction is going to need. Just like read the rightmost 2 bits into operand 2 and read all the 8 bits here into immediate as well. Right? Just use both. Just fill in both, even though you're only going to ever use one. Okay? So that's the idea. So you're not sure. Just depends on the instruction. So even though like print int only use operand 1, just set every one of them. All right? Just pretend that they're there. All right? So that you can just implement it one way and you're good to go. All right? So here's decode. You're going to have to extract the opcode bits, the dest bits, the operand 1 bits, operand 2 bits, and you're going to encode it as like registers, as these enums. So figure out how to use these enums and load them in, all right? And you're going to return this instruction I as you put stuff in it, okay? And then, yeah, extract operand 2 just as a register, and then also as immediate. They're the same rightmost 8 bits, though, all right? You can't have both, but we're just going to fill them in anyways, all right? So that's that part. What else? What else? So that's the decode. You'll probably want to... There's also a decode register. That's going to help you, right? Decode register, decode opcode. You can call both of these. So once you get the 8 bits of your opcode, right? That's just a character, right? Because it's 8 bits of your opcode. You can make a little helper function for yourself, helper method, I guess, that returns it as an opcode that's going to help you as you're doing the real decoding, all right? So only look at the rightmost 4 bits. The rest of the bits we don't care about. They could be set to 0 or 1. We still want to look at just the rightmost 4 bits to figure out what opcode we are. Same when you're decoding registers. You got the 8 bits that correspond to this chunk, but you're only actually going to look at the rightmost 2 bits, right? We don't care about the first 6. We don't need them. They could be anything. So if you see these, those are the registers that are being encoded, and you'll use those as helpers in your decode. I think that will be useful for you. Okay, so that's decode. And then what else? What else? So then you've decoded it, and then like execute memory and write back stages. That'll just be all in this run program method. All right. And so now it's just like based on the opcode of that instruction that I just decoded, how do I implement it? All right, so I have a lot of fix-me's that will help you. Here's some that I've already implemented for you. So I've made a helper function, first of all, helper method really, called getRegister. What it does is it goes, like given the register that you're trying to get out, it's going to give you that register back as, it's one of these, right? It'll give you one of these back, whichever one that was being encoded, as a reference, so that you could either use the value or change the value. All right, that's useful. And so if I go to that in the implementation, let me show that to you in the CPP file. If I just scroll up, here's the getRegister function. Taken and given the register, it gives you back which one. Okay, so like if it was reg 0, it's going to give you back R0 as a reference, so you can potentially set it using that call. All right, and so here I'm using getRegister. I've already implemented the execution and write back stages for the add register instruction like this. So what it uses, right, add register, what's it trying to do? Add register, you're going to read it off this page. Like it takes operand 1 and operand 2, not an immediate. It's going to take the 2 operand registers and add them up and put the answer in the destination register. All right, so here we are getting the destination register as an address, whatever it was. Here's the operand 1 value. Here's the operand 2 value, just using getRegister for all of that. See how seamless that is? That's pretty nice. And then I'm setting the destination register, whatever it was, to the sum of those 2 operands, the values of those 2 operand registers that I've saved ahead of time here. So that's how you implement the execution and write back stages of the add reg opcode. And this is all just in a loop, like whichever instruction it was, like I've done one again for you down here, like the print int, it's just like getting the register, printing the value, because all it's using is operand 1. All this is, right, if you think about it, all a CPU is doing as it's executing this is just in a big long loop forever. It is looking at the current PC instruction, incrementing it so that we know where to look next, decoding it, and executing it. And then we're just like in the while loop, we're looping, right? We're looping through every possible instruction. We're just doing this until the end of time, until the CPU is turned off. Get the next instruction out of PC, increment PC, execute that instruction in the decode, fetch, decode, write back. Fetch, decode, execute, memory, write back, potentially. All right, all those guys. And then the halt instruction stops the program. So if you see the halt instruction, it doesn't even use any operands or anything. It just stops the program, which for our simulator's purposes breaks out of our while loop. That's going to stop our execution. It turns off the CPU. I hope you can kind of see, you got to read this a few times maybe, but I hope you can kind of see how this is going to be executed. And you definitely now know why it's a multi-week lab now, don't you? All right. So yeah, that's kind of how that works. That's what you're going to be implementing. Yeah, all that fun stuff. The decoding is going to be fun, and you'll use a lot of bitwise operations. So do ask lots of questions, and do start early. All right. But to compile and test your stuff, you're going to do make simulator. I gave you the make file. And then to run your compiled simulator, you're going to run it like this with a compiled program. You'll be like program/countup.c45 without the without the .s, because this is the binary form of that file. Okay? So I think that is all that I wanted to say. You're going to have to read this a few times. It's one of those labs, all right? But all you're touching is cpu.cpp. So after you get all this stuff implemented, all these bad boys, oops. Once you get all this stuff implemented, you'll be able to enjoy the fruits of your labor. I promise it's so worth it. It's going to be such a nice feeling to see it finally work. And I'm here to help you. But like once you're ready to turn it in, you're just turning in that one file. That's all that you're writing, okay? So you use everything else, hopefully, with all of my helper fix me comments. You can get it working. And yeah, once you wrap your mind around it, it's not too horrible, but it is a lot of moving parts, all right? So definitely start early, ask lots of questions, and you'll be graded on all my sample programs. So that is a simulator for a CPU at a pretty low level. All of those different execution stages. It's very cool. You'll feel good once you get it working. Good luck. And yeah, I think that's all that I wanted to say. I'll see you in the next one.